there's a ratio of the number of chemicals in the equation. And the ratio is for every 4 ammonia, you need 5 oxygens, and you get 6 waters, and you get 4 nitrogen monoxides. So um, you know that you can count up individual numbers of atoms. This 4 ammonias, if the 4 ammonias really mean that there's 4 nitrogens and 12 hydrogens, but more importantly, the 4 ammonia really just mean that there's 4 of these ammonias. That's the name of this, is ammonia. And then there's also 5 oxygen molecules. It's true there's 10 oxygen atoms, but what's more important for these mole ratios is that there's 5 oxygen molecules. Similarly, there's 6 hydrogen or 6 water molecules and 4 nitrogen monoxides. So here's the deal. In total, a balanced chemical equation gives you ratios. It's a ratio of the individual chemicals. So the ratio of ammonia to oxygen to water to nitrogen monoxide is 4 to 5 to 6 to 4. And as a result of that, you can write conversion factors that relate those quantities. So, for instance, every conversion factor, the numerator and denominator are equal. In this equation, it's true that for every 4 ammonias, 4 like NH3s, you get 6 waters. So that equation can be written as 4 moles of NH3 over 6 moles of H2O. That's a conversion factor. The numerator and denominator are equivalent to each other because for every 4 ammonias, you get 6 waters. Or you can also write that as 6 moles of water is equivalent to 4 moles of ammonia. So the coefficients in the chemical equation are the values that you can use to relate quantities of chemicals. And now when we deal with chemical equations, it's actually important to write what the chemical is in the conversion factor to keep it straight. Now as a practice, you want to write that it's ammonia or water or nitrogen or something like that. So if you write the equations wrong, then you're going to balance the equation wrong. And if you have a poorly balanced equation, then you can't get a correct answer. So here's another example. This is magnesium hydroxide. And if you react it with sodium, sodium is above magnesium on the activity series. So you get a chemical reaction. The sodium replaces magnesium. You get magnesium and sodium hydroxide. So this is a regular, like, run-of-the-mill single replacement reaction. And what I see, what's true in this equation, is that for every 1 magnesium hydroxide, you've got to have 2 sodiums. And as a result of the reaction, you get 1 magnesium and 2 sodium hydroxides. So the ratio of chemicals, and we don't write the 1 because we know there's just one of them, but the ratios are 1 to 2 to 1 to 2. For every 1 magnesium hydroxide, you need 2 moles of sodium. And when you have that right ratio, the equation will go to completion and you don't have any stuff left over as a reactant, and you get all the products you're looking for. It's the same as it's like a recipe. You're putting different proportions of stuff together and you get the final product. It's like you might know if you're making cookies that you need flour, you need sugar, you need chocolate chips, and you need baking soda, but you better not weigh out equal amounts of them because you're going to get some terrible cookies. You have way too much baking soda. So here are some examples of mole ratios. The mole ratio could be 1 mole magnesium hydroxide to 2 moles of sodium. And usually we write them like as fractions in a parenthesis. Or for every 1 mole of magnesium is 1 mole of magnesium hydroxide because there's 1 and 1. Or you could write 1 mole of magnesium hydroxide is good for 2 moles of sodium hydroxide. You can write other ones. You can say for every 2 moles of sodium hydroxide that we need, we're going to need 2 moles of sodium. That's another ratio, because for every 2 sodium hydroxide, you need 2 sodiums. You can also write this upside down as for every 2 moles of sodium, you get 2 moles of sodium hydroxide. And of course, 2 over 2 is just 1, so whatever amount of sodium is the same as the amount of sodium hydroxide you get as a quantity, not as a mass, but as a quantity. So there's actually like, I don't know, let me think. It'd be 1, 2, 3, 4, 5, 6. There's 12 different mole ratios you could write from this equation with 4 different chemicals. Okay, so here, just a mole to mole conversion is a simple example. If I want to convert the quantity 4 moles of magnesium hydroxide into moles of magnesium, I can write 4 mole, oh, my thing just messed up. 4 mole MgOH2, and then write a conversion factor, and I'm trying to convert from moles of magnesium hydroxide into moles of magnesium. So because I started by writing moles of magnesium hydroxide, that's the unit that has to go in the denominator, MgOH2. And I'm trying to convert into moles of magnesium. And what these numbers are here is just whatever the coefficients are in the equation. And in the equation, this is a balanced equation. For every 1 mole of magnesium hydroxide, there's 1 mole of magnesium. So this reaction, or this arithmetic is not hard. 4 times 1 divided by 4 is just 4 moles of magnesium. Because in the equation, the ratio of magnesium hydroxide and magnesium is 1 to 1, no matter what quantity magnesium hydroxide you start with, you get the same quantity of magnesium. But if I want to convert like 4 mole magnesium hydroxide into mole of sodium hydroxide, the question is, if I have 4 moles of magnesium hydroxide, and I want to know how much sodium hydroxide I end up with, well, in the equation, there's only 1 magnesium hydroxide. It is understood to be a 1 out front. And for every 1 magnesium hydroxide, there are 2 sodium hydroxides, NaOH. 4 times 2 is 8, NaOH. So what the chemical equation just tells you when it's balanced is what the ratio of the quantities, and those quantities could be numbers of atoms or they could be quantities in moles. And most of the time, these conversion factors are very easy. They're always just going to have integers because we just use integers to balance chemical equations. So that's the basis of how the conversions go. All right. So this the worksheet you picked up on the way in. These are like some to practice about relating quantities of chemicals. The first one, it's hydrogen plus oxygen makes H2O. And you should be able to balance that equation pretty easily. The hydrogens look like they're okay to start with. There's 2 hydrogens on each side, but the oxygens are not balanced. So to balance the oxygens, you got to put a 2 on the right-hand side, but then that unbalances the hydrogens. So it turns out that if you burn hydrogen in the presence of oxygen, you get water. Hydrogen fuel cells are one way to make electricity. There's been talk from time to time, on and off, about converting to, primarily using hydrogen fuel cells to like power vehicles and stuff. But we need a good distribution system for hydrogen. But you take hydrogen and oxygen and you can make electricity and you make water as a waste product. And what that equation tells you is that in order to make water at all, you must have 2 hydrogen molecules. If you only have 1 hydrogen, you cannot make any water. You need a minimum of 2 hydrogens along with 1 oxygen to be able to even get to water molecules. So you've got to make water two at a time. So if you have 2 moles of oxygen, how much water could you make? So how that works is if you have 2 moles of oxygen, this is actually like a quantity that you have. Like you have 2 moles of oxygen. And let's say you have plenty of hydrogen. The question is, how much water can you make? So how much water you can make depends upon what the mole ratio is. And in this equation, for every 1 oxygen, you get 2 waters. So this factor is what we call the mole ratio. And because we start with a quantity, like you have 2 moles of oxygen, this moles of oxygen has to be the unit in the denominator. And we're trying to figure out how many moles of water we end up with. So moles of water goes in the numerator. And all you put in there is just the coefficients from having balanced the equation. This 2, or let's see, we've got 1 oxygen and 2 waters. So it's 1 mole of oxygen in the denominator, 2 moles of water in the numerator. 2 times 2 is 4. So if you have 2 moles of oxygen, you can make 4 moles of water. As long as you have enough hydrogen. If you don't have enough hydrogen, then you won't get the 4 moles of water. And we'll deal with how you figure that out. It's called, and it's one of the reactants could be a limiting reactant. It's like if you buy a pack of 10 hot dogs and you get a pack of 12 hot dog buns, the limiting factor is the hot dogs. You can make 10 hot dogs. You have 2 buns left over. All right, so the second one, balance that equation. We have aluminum and HCl. Make aluminum chloride and hydrogen. You did this reaction. We put some hydrochloric acid in with some aluminum, made aluminum chloride as a solution, and you got some hydrogen gas. The bubbling is an indication that a chemical equation or chemical reaction is happening. So the aluminums are already balanced, but the hydrogens are not okay. So it looks like you can put a 2 in front of the HCl, except then the chlorines are no good. You got 2 chlorines on the left and 3 on the right. So it turns out that the, least common multiple of the 2 and 3 there is 6. So you actually need to have 2 aluminum chlorides, and then you got to have 6 HCl's. And there's going to be 3 hydrogens and 2 aluminums. Yeah, you can't do any better than that. That's it. So the ratio of the chemicals in the equation are 2 to 6 to 2 to 3. To make the equation go, to make the reaction go, you've got to have 2 aluminums for every 6 hydrochloric acids as ions in solution. You get 2 aluminum chlorides and 3 hydrogens. Those are the ratios of the chemicals that take place. So there's a bunch of different ratios, and you don't have to write them all, but one ratio is like 2 mole of aluminum to 6 mole of HCl. That's 1 mole ratio. You can also have like 2 mole of aluminum to 2 moles of aluminum chloride. Or, you can have 2 moles of aluminum to every 3 moles of hydrogen. You can have 6 moles of HCl to every 2 mole of aluminum chloride. You could have 6 mole of HCl to every 3 mole of hydrogen. And then the last one is like, kind of didn't leave him a lot of space. 2 mole of aluminum chloride to every 3 mole of hydrogen. And you can also have, the reciprocals of all of those. You could have, 6 mole HCl over 2 moles of aluminum. You just flip them upside down. So from any one chemical equation, you can relate quantities in 12 different ways if it's a single replacement reaction. So all you're really doing is just taking, like, if it says 6 HCl, that is represented as 6 moles of HCl, and then 2 aluminum chlorides is represented as 2 moles of aluminum chloride. And then how the ratios are useful is whatever chemical you're converting from goes in the denominator, whatever chemical you're producing goes in the numerator. So in part B of that, how many moles of aluminum metal are needed to make 3.3 moles of aluminum chloride? I want to make 3.33 moles of aluminum chloride. How many moles of aluminum do I need? So that is this conversion factor here that I just wrote. The moles of aluminum chloride go in the denominator, and in the equation, there are 2 aluminum chlorides, and you need 2 moles of aluminum for that. So because the ratio of aluminum to aluminum chloride is 2 to 2, that's the same as 1 to 1. To make any amount of aluminum chloride, you need the same quantity of aluminums. So that's just 3.33 moles of aluminum. But how much HCl you need is a different quantity. So if you want to make 3.33 moles of aluminum chloride, the amount of HCl you need is different. There are 6 moles of HCl for every 2 moles of aluminum chloride. So, I mean, that's 9.99, but it's, pretty near 10. So if my goal is to make 3.33 moles of aluminum chloride, I must have 3.33 moles of aluminum and 9.99 moles of HCl. Here you can see the ratio is like 1 to 3 times more HCl than aluminum. And in the equation, as a balanced equation, it looks like I need a ratio of 2 to 6, which is the same as 1 to 3. I need 3 times more HCl than I need aluminum. And they don't have the same mass, of course. So not only are there different quantities of the reactants I need, but because the reactants have different masses, I need different masses of them as well. And HCl is a whole other thing because you don't actually weigh out HCl because that's an acid in solution. And we have a way to deal with it in an equation as a concentration in a unit called its molarity. This is like the heart of chemistry, doing chemical reactions, but it's taken a long time to get to writing and doing chemical equations and figuring out quantities because we had to know everything about individual atoms, know how compounds go together, know how different equations are written, know how to balance equations. And now we'll relate masses and moles to these quantities. And in the end, you can, hear the names of 2 chemicals and predict how much of each you need to start with and how much of each of the products you're going to end up with. That's the whole basic plan. All right, number 3. So there's a description. Aluminum bromide and sodium hydroxide react to form aluminum hydroxide and sodium bromide. And the chemical formulas are already written, but you can write the equation and then we have to balance it. So you got aluminum bromide and sodium hydroxide react to form aluminum hydroxide, AlOH 3, that's the solid, and sodium bromide, NaBr. Turns out, if you look up on the solubility chart, this aluminum hydroxide, that's the solid. The sodium bromide, that's aqueous. These are also aqueous. So that's a common double replacement reaction, and it's not balanced. The hydroxides are what's wacky. So you got to have 3 in front of the sodium hydroxide, and then you put a 3 in front of the, a 3 in front of the sodium bromide, and now we're okay, because you got 1 aluminum on each side, 3 bromines on each side, 3 sodiums on each side, and 3 hydroxides on each side. So writing the equation out and balancing it has to be correct. If that's incorrect, then you cannot get correct answers. So how many moles of sodium bromide, how much sodium bromide is formed if we start out with 1.55 mole of aluminum bromide? So you can use a conversion factor, and this unit that you start with, we had 1.55 moles of aluminum bromide. Moles of aluminum bromide goes in the denominator, and we want to figure out how much sodium bromide, NaBr. And in the equation, the ratio is 1 to 3. So for every 1 mole of aluminum bromide, you get 3 moles of sodium bromide. So 4.65 moles sodium bromide. All right, I gotta say a thing about significant figures. So you might look at this problem here and say, well, the 1.55 has 3 significant figures or 3 significant digits, but the 3 and the 1, those only have 1 each. But these are whole number ratios that aren't measurements. They're ratios in the equation, and they're perfect. So the only thing that affects numbers of significant figures are the things that have been measured. The 1.55 mole is a quantity that we're either trying to produce or we've measured out. The 3 and 1, that ratio, this mole ratio, it has like an infinite number of significant figures, sig figs. So because this had 3 significant figures, I write SF for significant figures, you get 3 significant figures here. The numbers of significant figures are exactly the same. You don't like reduce the number of significant figures because of the 3 or the 1. Those are, they're perfect. They're exactly like that. So it's actually really nice that this world we live in, that when chemical reactions happen, they're whole quantities with whole number integer ratios, and those ratios are usually relatively small values. And you might think if you get this figured out, it might be like, oh, that's a lot of math or a lot of stuff to write. I can just see that it's 3 times more sodium bromide than aluminum bromide. But it turns out these mole ratios here, converting from moles to moles, isn't that exciting. But it's when we relate masses of aluminum bromide to masses of sodium bromide that you include the mole ratio in the steps, and it makes the math easier and things a little easier to conceptualize. All right, so on the back, try that last one, that number 4, methane and oxygen react in a combustion reaction. So methane, its common name is natural gas. Natural gas, if you have like a gas stove or gas range or gas furnace in your house or gas fireplace insert, that's what it runs off of. That's the gas that comes into our labs so we can run our Bunsen burners. And River Valley transit buses are natural gas. Our buses in the city do not run on diesel fuel or gasoline. They run on natural gas. It's compressed natural gas, and it's a lot cleaner burning. Like our old buses ran on diesel fuel, and they'd start off from a stop sign, and the big black smoke would pour out, and they were pretty noisy. Uh, the newer buses are all run on natural gas, and you can buy if you have a natural gas vehicle, you can buy natural gas on Third Street. There's only one place in town on Third Street, right by the bus garage for the city. It's like by the mulch pile. Like as soon as you go over the Third Street bridge, uh, like the recycling center's on your left. You go across the bridge, water plant's on the right, mulch pile, and the bus garage is on the left. And you can buy natural gas. It's like $1.99 per gallon equivalent, but not many vehicles use compressed natural gas. Ford made a Ranger a few years ago. Honda made a Civic that used compressed natural gas. You can get them. They're mostly for larger and fleet vehicles now. All right, so that's the equation. All combustion reactions, the products are CO2 and H2O. And this equation is not balanced to start out. So you got to put a 2 in front of the H2O and, I don't know, a 2 in front of the O2. So now there's 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens on each side. So the ratio is 1 to 2 to 1 to 2. For every 1 methane, you need 2 oxygens, and you get 1 carbon dioxide, and you get 2 water vapors. So that's the balanced chemical equation. You can't get anything else right unless the equation is balanced correctly. So anyway, B, how many moles of methane are needed to produce 3 times 10 to the negative fourth moles of carbon dioxide? So the quantity we're trying to determine is 3.5 times 10 to the negative fourth mole of CO2. We need to know how many moles of methane do we need. So the moles of CO2, which is the quantity we start with, has to go in the denominator. Moles of methane, that's the CH4, goes in the numerator. And the ratio is 1 to 1. For every 1 carbon dioxide, you needed 1 methane. That's how you'd write it out. But you can also look pretty quickly. It's just going to be 3.5 times 10 to the negative fourth moles of methane. Because no matter what quantity of methane, you get exactly the same quantity of CO2. How many individual molecules is this? So if you take 3.5 times 10 to the negative fourth moles of anything, a mole of anything is 6.02 times 10 to the 23rd molecules. So let's see, 3.5 negative fourth times 6.02 times 10 to the 23rd. So it'd be like 2 significant figures, 2.1 times 10 to the 20th molecules. So you can relate quantities in moles to number of molecules. You can also separately relate this quantity in moles to a mass in grams. So if you have 3.5 times 10 to the negative fourth mole of methane, and you want to know what that mass is going to be, 1 mole of methane has a certain mass. And you can figure out that mass pretty easily. For methane, you've got 1 carbon, which is 12.01 grams. So that's 12.01. And you've got 4 hydrogens. Each hydrogen is 1.01 gram. So that's 4.04 grams. You get 16.05 grams. So the formula mass for methane, or the molecular weight, is 16.05 grams. That's how we're going to relate mass quantities to molar quantities. 3.5 times 10 to the negative fourth times 16.05. Syntax error. Oh, I see what happened. 0.0056. These zeros are not significant, so the 5 and 6 are significant figures. That's some kind of mass in grams. The mass of CO2 is different because so although the quantity of methane and CO2 are the same, because CO2 has a different mass, the mass of CO2 is going to be different than the mass of the methane. But in the end, the law of conservation of mass will always work out that the mass of methane plus the mass of oxygen, those two masses together, have to be exactly the same as the mass of CO2 and H2O together. You can't create or destroy matter or create or destroy mass. You can just, rearrange it or change it around in chemical equations. All right, so those are good things. The next things we got to deal with include like converting moles into volumes for gases and moles into volumes based upon concentrations for solutions. Then we'll be able to go back to every reaction we've ever done before and relate relative quantities.